So first off is a common base, BJT. So remember that the base is grounded, the input is in the emitter, and the output is in the collector. Now in a common base, the current gain should be around 1 or 0.99, and here you can have a current gain of 0.99. And here's the voltage input, and here's a voltage output, and you can see that there is a voltage gain. Calculating it, you will get a voltage gain of around 2.5. Now to check these values, you have to manually solve the circuit using approximation formulas. Now, shown here, using these formulas, you get the parameters of the circuit, and with AC analysis, you can get the current gain and then the voltage gain. Now here's the voltage gain, which is 2.48, and a current gain of 0.99, which means that this circuit here is correct. Now, moving on. The graph of the voltage gain should also be remembered. Now that the input and the output are in phase, but the output has a bigger amplitude, representing the voltage gain of the BJT common base. So there you go. That's a common base BJT.
So this is a common collector amplifier where the input is at the base and the output is at the emitter. By getting these, we can get IB, IC, and IE. And with these, we can get VCE to confirm that this circuit is an amplifier. So we should proceed to the AC analysis part, where by using IC and IE and IB, we can get the current gain and the voltage gain. So going to the simulations, we can see that at the input, the current here is close to the commutation, which is 19.2 microamperes, and at the output is 1.94 milliamperes. So as you can see in the oscilloscope, the blue is the output and the red is the input. So going to the voltage gain, the input and the output has minimal difference, so that means the voltage amplification is very little.
This is a BJT transistor, and you can notice here that this is a voltage divider, meaning you need to get the RTH by getting the parallel value of R1 and R2, and then VTH by using voltage division, and then draw the equivalent circuit and use this loop to get IB, and use algebra to get the value of IB, and then IC is equal to beta IB, IE is equal to beta plus 1 IB, and then to get VCE, use the loop from VCC to the common ground. Beta RE is equal to 170.16. And then to get Z in, you need to series BRE and the resistor at the emitter, and then parallel it to the RTH, which is this one. And Z out is the resistor at the output, and then the current gain is equal to negative beta, and AV is equal to negative 444.12. This is the simulation of the BJT a while ago, and you can notice here that there is a voltage gain, and if you check the waveform, the wave of the output is 180 degrees out of phase with the input, which is correct for a common emitter. And for the current gain, you can see here that the current at the output increased. Current at the base, the collector, and the emitter are the same with the initial calculation.
This is a simple power supply circuit. In this circuit, you can find a transformer with a turns ratio of 10:1, a full wave bridge rectifier, a voltage regulator, and a load resistor. The input VRMS is 22 volts, and the output DC voltage is 5.151 volts. So here is the waveform response. Let's now proceed with the calculations. The transformer has a turns ratio of 10:1. The primary voltage is 220 volts and the secondary voltage is 22 volts. For the full wave bridge rectifier, to get Vmax, multiply the VRMS, secondary voltage 22 volts, by square root of 2. Now the Vmax is 22 square root of 2 volts. The DC value is obtained from multiplying 0.636 to our Vmax, which is 22 square root of 2, and now our VDC value is 19.79 volts. For the filter, to obtain the voltage ripple peak to peak, it is 22 square root of 2, or the Vmax, over the resistor value times the capacitance value times twice the frequency, and therefore we have 259.27 millivolts. For VDC, subtract RPP over 2 to R Vmax, and now we get 30.98 volts. For the Zener, which is our voltage regulator, we use in this part is the ideal Zener. The PZ max is 1 watt. The voltage of the Zener is 5 volts. When the voltage is at 30.98 volts, IT is 0.031 amperes or 31.98 milliamperes. The IL is 5 milliamperes, and therefore if we compute the IZ max, which is equal to 200 milliamperes, and the IZ min, which is equal to 20 milliamperes, it is in between IZ max and IZ min. Therefore, it satisfies that the voltage of our Zener is 5 volts, and it is also the output voltage. The actual voltage that we obtained from the simulation is 5.151 volts.